Somewhere out there, in the deepest, darkest reaches of space, exists a galaxy so incomprehensibly massive that when astronomers first calculated its true size, they thought their instruments had broken. They checked their math again and again, and then they realized they hadn't made a mistake at all. We're talking about a galaxy with 6 million light-years of diameter. A galaxy that contains up to 100 trillion stars. More stars than every grain of sand on every beach on Earth. More stars than you could count if you spent your entire life saying one number per second, and your descendants continued for thousands of generations after you were gone. And here's the truly mind-bending part. This galaxy is still growing. It's still feeding on smaller galaxies, swallowing them whole, becoming more massive by the year. For billions of years, it's been this cosmic cannibal, slowly consuming everything in its path, accumulating power, mass, and mystery. The question isn't just how big it is. The question is, what does a galaxy this enormous tell us about how the universe actually works? What happens when you build a structure so large that it challenges the very laws of physics itself? And what does it mean that we keep discovering galaxies that are even more extreme than the last one? Tonight, we're diving deep into one of astronomy's greatest mysteries. We're visiting the edge of cosmic comprehension. And we're asking a question that might change how you see your place in the universe forever. Welcome to the story of IC 1101, the largest galaxy ever discovered. A structure so vast that if you tried to travel across it at the speed of light, it would take you longer to cross than the sun has existed. Longer than life has existed on Earth. If you're new here, welcome. I'm your guide through the cosmos. And if you've been with us before, thank you for coming back. This channel exists because of curious minds like yours. Because some of us can't help but ask the big questions. Like, how big can something actually get? And what does it mean when we find something that breaks all our previous assumptions? Over the next couple of hours, we're going to explore not just a galaxy, but a profound puzzle at the heart of astronomy. We'll trace how astronomers even discovered this object. We'll dig into the physics of how something this massive could form. We'll explore the dark matter empire that's holding it all together. We'll examine what lives inside it. And we'll confront some genuinely unsettling implications about the future of galaxies and perhaps our own. Here's what you need to know going in. IC 1101 is 1.07 billion light-years away. That means the light we're seeing from it left that galaxy over 1 billion years ago. We're looking at it as it was before the sun even existed. And what we're seeing challenges everything we thought we knew about how galaxies reach their limits. Throughout this exploration, we're going to encounter some real mysteries, some genuine unknowns. Because despite decades of observation and computer simulation, we still don't fully understand how a structure this large could assemble itself. We don't understand why it stopped growing when it did. And we definitely don't understand what its ultimate fate might be. So if you want to spend the next few hours pondering the edges of reality, wondering about structures so large they barely fit in human consciousness, and exploring the deep mysteries that keep astronomers awake at night, then stick with me. Let's begin where every great discovery begins, with a simple observation that led to something extraordinary. To understand IC 1101, we first need to understand how we even found it. And that story begins not with IC 1101 itself, but with a much simpler question. What is a galaxy? For most of human history, we didn't know. What we thought were clouds of gas floating in space turned out to be entire universes unto themselves. Island universes containing billions of stars. And it took us until the 1920s to figure this out. Edwin Hubble was the astronomer who cracked this mystery. Using the 100-inch telescope on Mount Wilson in California, he peered at what most astronomers called the Andromeda Nebula, just a fuzzy patch of light. But inside that patch, Hubble found something extraordinary. Individual stars that pulsed and brightened in a regular pattern. These were Cepheid variables, stars whose pulsation tells astronomers their true brightness. Once Hubble knew how bright these stars actually were, he could figure out how far away they must be to appear as dim as they did. The answer stunned the astronomical community. Andromeda wasn't inside our galaxy. It was way beyond it. It was its own galaxy entirely, separated from us by millions of light years. This discovery changed everything. If Andromeda was a separate galaxy, then all those other fuzzy patches might be galaxies too. And so began one of the greatest surveys in astronomical history. Astronomers around the world started cataloging these objects, measuring their distances, trying to understand their properties. What they discovered was astonishing diversity. Some galaxies were spirals, with elegant, rotating arms made of gas and dust. Others were ellipticals, smooth and featureless, like cosmic footballs. And within the category of elliptical galaxies, there was an enormous range of sizes. Most elliptical galaxies were relatively modest, containing maybe a few billion stars. But every so often, astronomers would find a giant, a truly colossal elliptical galaxy. And these giants had a strange tendency to sit at the centers of galaxy clusters, surrounded by hundreds or even thousands of smaller galaxies, all orbiting around them. We call these central giant ellipticals CD galaxies, which stands for supergiant diffuse. The name captures something essential about their nature. They're gigantic, but their light is spread so thin across so much space that they're actually very faint. You could point a telescope at IC 1101 right now and see it, but it wouldn't look that impressive. It's not bright. It's just impossibly, almost insanely vast. IC 1101 itself was first cataloged in the late 1900s. Given that designation in the Index Catalog, a supplement to the new General Catalog of Astronomical Objects. It appeared as just another faint fuzzy blob in the constellation Virgo, unremarkable to most observers. Nobody initially realized they were looking at what would become the largest galaxy ever measured. It took decades of better telescopes and better measurement techniques before astronomers realized what they had. And when they did, they had to face a new problem. How do you even measure something this big? See, galaxies don't have sharp edges. They don't have a boundary like a planet does. The density of stars gradually gets thinner and thinner as you move outward from the center. At some point, the starlight becomes so faint that it blends into the background. So where does one galaxy end and empty space begin? It's surprisingly arbitrary. Different astronomers use different definitions. Some measure the radius that contains half the galaxy's light. Some measure out to a specific brightness threshold. Some try to include the entire dark matter halo that extends far beyond the visible stars. Depending on which definition you use, IC 1101 could be 4 million light-years across, or 6 million, or even larger. But all definitions agree on one thing. IC 1101 is incomprehensibly vast. It's not just the biggest galaxy known. It's so much bigger than any galaxy we've ever seen that it exists in a different category altogether. To put this in perspective, imagine if you could shrink the Milky Way down to the size of a quarter. IC 1101 wouldn't be a dollar coin or a dinner plate. It would be the size of a building, a structure the size of a football stadium, compared to a quarter. That's the scale difference we're talking about. But here's what makes IC 1101 truly special. It's not a unique freak of nature. There are actually a handful of other galaxies nearly as large. We'll explore those later, but IC 1101 holds the crown. It's number one, the record holder. And yet, despite being discovered over a century ago, despite being studied intensely by astronomers around the world, IC 1101 still holds secrets. We still don't fully understand how it got so large. We don't understand how it avoids tearing itself apart under its own gravity. And we certainly don't understand what comes next in its evolution. These mysteries are what drive this exploration. Because IC 1101 isn't just a curiosity. It's a window into how the universe actually builds its largest structures. It's a test of our understanding of gravity, of galaxy formation, of the fundamental rules that govern the cosmos. Let's talk about something that might seem simple, but is actually extraordinarily complex. How do astronomers measure the distance to IC 1101? This is crucial because size means nothing without distance. A coin held close to your eye can block out the sun. So is the coin bigger than the sun? Of course not. You're just confusing apparent size with actual size. The same problem plagued astronomers for centuries. They could see that some galaxies were brighter or dimmer than others. They could measure the angles these galaxies subtended on the sky. But without knowing how far away they were, they couldn't figure out how truly large any of them actually were. Hubble solved this problem for nearby galaxies using Cepheid variables. But for IC 1101, which is over 1 billion light-years away, that technique doesn't work anymore. The individual Cepheids are too faint to see, even with our most powerful telescopes. So astronomers had to develop different techniques. And the primary one they use for giant elliptical galaxies, like IC 1101, is something called the Faber-Jackson relation. Here's how it works. In an elliptical galaxy, the stars don't all move in the same direction like they do in spiral galaxies. Instead, they move chaotically in every direction, like bees swarming randomly in 3 dimensions. Some stars move very fast relative to the galaxy's center. Others move slower. The average speed of all these stars, what astronomers call the velocity dispersion, tells you something crucial: how massive the galaxy is. A more massive galaxy has a stronger gravitational pull, so its stars move faster on average. It's simple physics. More gravity equals faster motion. And here's the key. The velocity dispersion of a galaxy's stars also correlates with its luminosity. Massive galaxies tend to be brighter. The relationship is actually quite tight, which means if you measure how fast the stars are moving, you can predict how bright the galaxy actually is. And if you know how bright it actually is, and you measure how bright it appears to be from Earth, then you can calculate the distance. For IC 1101, astronomers have measured a velocity dispersion of about 350 kilometers per second. That's incredibly fast. For comparison, the Sun orbits the center of the Milky Way at about 230 kilometers per second. Stars in IC 1101 are moving about 50% faster. That tells you how massive this galaxy is. Using the Faber-Jackson relation, this velocity dispersion predicts that IC 1101 is intrinsically one of the brightest galaxies in the entire observable universe. When astronomers compare that prediction to how bright IC 1101 actually appears to us, they calculate a distance of about 1.07 billion light years. But that's not the only distance measurement technique astronomers use. Another approach relies on something called redshift. Due to the expansion of the universe, distant objects are moving away from us. And as they move away, their light gets shifted toward longer wavelengths, toward the red end of the spectrum. This effect is called redshift. And the amount of redshift tells you how fast an object is receding, which, for distant galaxies, tells you how far away it is. This technique relies on something discovered by Edwin Hubble himself, called Hubble's law. Basically, the farther away a galaxy is, the faster it's moving away from us due to cosmic expansion. And this relationship between distance and recession velocity is remarkably consistent. For IC 1101, astronomers have measured the redshift and calculated a distance of about 320 megaparsecs, which translates to roughly 1.04 billion light years. And here's what's remarkable. That's consistent with the distance calculated from the Faber-Jackson relation. Two completely independent measurement techniques give essentially the same answer. That's how you know you're onto something real. But I need to be honest, these measurements aren't perfect. There's uncertainty. The distance could be as close as 960 million light years or as far as 1.2 billion light years. When you're measuring something so far away, some uncertainty is inevitable. But that's not the point. The point is that we've pinned down IC 1101's distance well enough to say something remarkable. It's so far away that the light we're seeing from it left that galaxy over 1 billion years ago. We're looking at IC 1101 as it was before the Sun even formed, before Earth existed, before life evolved on any planet in our solar system. Now, once we know the distance, we can convert the apparent size of IC 1101 on the sky into an actual physical size. This is where things get genuinely mind-bending. IC 1101 spans about 1.2 to 2 arcminutes on the sky. If you don't know what an arcminute is, imagine the full moon. The full moon is about 30 arcminutes across. So IC 1101 takes up about 1/25th to 1/60th of the moon's width on the sky. That doesn't sound that big, does it? But at a distance of over 1 billion light years, that modest angular size corresponds to an absolutely staggering physical size. Here's where it gets real. IC 1101 is approximately 6 million light years in diameter. Think about that number, 6 million. If you wanted to travel across IC 1101 at the speed of light, it would take you 6 million years. 6 million years? The human species has only existed for a few 100,000 years. We'd have to time travel forward 40 times further into the future just to reach the other side of this galaxy. To put it another way, the distance from the Milky Way to Andromeda, which is one of the great cosmic distances that should illustrate how spread out galaxies are, is about 2.5 million light years. IC 1101 is more than twice that wide. It's so large that it's wider than the entire gap between our galaxy and our nearest large galactic neighbor. And this is the effective radius, the radius containing half the galaxy's light. The outer edges, where the starlight becomes too faint to detect reliably, might extend even further. Some estimates suggest IC 1101 could be even larger than 6 million light years across. Now let's talk about mass. Because size isn't the only thing that's extreme about IC 1101. The mass is just as staggering. Measuring the mass of a galaxy is trickier than measuring its size. We can't just put it on a scale. We have to rely on gravity. The stars in the galaxy move at certain speeds. We can measure those speeds. And the speeds tell us how much mass is actually pulling on those stars. Here's the thing though. When astronomers measure how fast stars move in IC 1101, especially the stars far from the center, they find something startling. The stars are moving way too fast to be held in orbit by just the stars and gas we can see. There has to be additional mass. Invisible mass. Dark matter. And the calculations show that IC 1101 has a total mass of roughly 100 trillion solar masses. That's one followed by 14 zeros. 100 trillion times the mass of our sun. Meanwhile, the Milky Way, which is already a giant galaxy, has a total mass of only about 2 trillion solar masses. IC 1101 is about 50 times more massive than our entire galaxy. But here's something that really drives home how extreme IC 1101 is. About 85% of that mass is dark matter, invisible stuff we can't see. Only about 15% of IC 1101 is ordinary matter, the kind of matter that makes up stars and planets and you and me. And get this, the stellar mass, just the stars themselves, is estimated at around 10 to 20 trillion solar masses. That means IC 1101 contains somewhere between 50 trillion and 100 trillion individual stars. More stars than there are grains of sand on every beach on Earth combined, possibly by a factor of 10. Think about that. You could spend your entire life saying one number per second, and you still wouldn't count to 100 trillion before you died. You'd need your ancestors going back to the dawn of human civilization, all of them counting continuously without sleep to get through that number. And IC 1101 contains that many stars. packed into a structure so large that light takes millions of years to cross it. It's almost incomprehensible. So how do we measure all this? Astronomers use several techniques. They study the motions of the stars themselves. They look at how the galaxy bends light from objects behind it, using something called gravitational lensing. They observe the hot gas that surrounds giant galaxies like IC 1101, which radiates X-rays that tell us about the gravity field. And all these techniques paint the same picture. IC 1101 is incomprehensibly massive. If you were standing outside IC 1101, looking in at its structure, what would you see? First, there's the stars. 100 trillion of them. But here's what's surprising. They're almost all old, ancient. Most of the stars in IC 1101 are red dwarfs. Small, cool, thin stars that burn their fuel incredibly slowly. They're the cosmic equivalent of a banked fire that will glow for trillions of years. There are also red giants, old stars that have swelled up as they age, shedding their outer layers into space. There's very little of what we call active star formation happening in IC 1101. No brilliant blue stars being born. No dramatic nebulae where new stars are coalescing from gas and dust. IC 1101 is a galaxy that is largely finished making new stars. In fact, the spectrum of IC 1101, the light split into its component wavelengths, shows all the signs of extreme age. The absorption lines in the spectrum match up with what we see in ancient stellar populations. And when we estimate the ages of the stars in globular clusters orbiting IC 1101, we get ages around 12 to 13 billion years. These are some of the oldest stars in the universe. What this means is that IC 1101 formed most of its stars in the first few billion years after the Big Bang, when the universe was smaller, denser, and full of gas and dust, ready to form new stars. Since then, it's been coasting. A relic of the early universe. A fossil. But here's the crucial thing. The stars, impressive as they are in number, aren't the dominant component of IC 1101. They're only 15% of the mass. The rest? Dark matter. Dark matter is one of the great mysteries of physics. We know it's there. We know it's real, but we don't know what it is. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It interacts with ordinary matter only through gravity. And gravity is its only fingerprint. But that fingerprint is unmistakable. Without dark matter, galaxies would fly apart. The stars move too fast to be held in orbit by just the visible matter. Without dark matter, galaxy clusters would dissolve into the expanding universe. Without dark matter, the first stars and galaxies would never have formed in the early universe. Dark matter is the gravitational scaffolding that holds the cosmos together. In IC 1101, the dark matter forms a halo around the galaxy. A vast, invisible sphere of this mysterious substance that extends far beyond the visible stars, perhaps 10 million light-years or more from the center. This halo is so massive that it overwhelms everything else. It dominates the galaxy's gravity. It's what holds all those 100 trillion stars in orbit. Imagine a sphere 10 million light years in radius, invisible, filled with matter we don't understand, so massive that it holds in place 100 trillion stars, each one containing worlds and possibilities we can never fully comprehend. That's what IC 1101 is. A structure so large, so massive, so fundamentally alien to human experience, that it exists almost in a different category of reality. Inside all this, toward the center, sits something even more extreme, a supermassive black hole. Estimates suggest it contains 40 to 100 billion solar masses. That's more massive than most galaxies. An object so dense that not even light can escape it, sitting at the heart of this incomprehensible giant. The stars in IC 1101 aren't organized like the stars in the Milky Way. In our galaxy, stars move in a relatively organized way, orbiting in a flat disk, all rotating in roughly the same direction. But in IC 1101, the stars move chaotically, in every direction, on elongated orbits that take them through the galaxy's interior at random angles. It's a chaotic swarm rather than an organized system. This randomness tells us something crucial about IC 1101's history. It tells us that it wasn't formed as a single, coherent structure. Instead, it was built through a series of violent events, collisions between galaxies that scrambled everything together, destroying any organized motion and replacing it with chaos. And IC 1101 has barely any gas or dust left. Most galaxies have gas. It's the raw material for making new stars. But IC 1101 has almost none. It's been either consumed into stars, or blown away by stellar explosions, or stripped out by interactions with other galaxies. So what we're looking at when we observe IC 1101 is not a galaxy in its prime, actively forming new stars and evolving. We're looking at a galaxy in its old age, a structure that reached maturity billions of years ago and has been slowly cooling and dying ever since. But before it aged, IC 1101 must have had an incredibly violent youth. And that's where things get really interesting. How does a galaxy grow to be so incomprehensibly large? The answer is one of the great achievements of modern astronomy. And it involves a process so relentless, so patient, so fundamentally powerful that it reshapes our entire understanding of how the universe builds structure. The process is called hierarchical merging. And here's the basic idea. Galaxies don't exist in isolation. They form in groups and clusters. And over billions of years, gravity brings them together. When they collide, they merge. Two galaxies become one, and the resulting galaxy is larger, more massive, more dominant than either of the originals. In the early universe, this process happened constantly. Small galaxies formed first. They quickly grew, merging with other small galaxies to become medium galaxies. Those medium galaxies merged with each other to become large galaxies. Those large galaxies collided to become giants. And the giants in dense clusters absorbed all their neighbors to become the ultramassive structures we see today. IC 1101 sits at the center of the Abell 2029 cluster, a region of space so densely packed with galaxies that there are hundreds of them all orbiting in the same gravitational field. Imagine being in the middle of a cosmic city, where every light you see is an entire galaxy, each containing billions or trillions of stars. That's what the center of the Abell 2029 cluster is like. And IC 1101 is the king of that city, the most massive object, the gravitational anchor around which everything else orbits. But IC 1101 wasn't always a king. Billions of years ago, it was just another galaxy, maybe larger than average, but nothing approaching its current size. But it had something that changed everything. It was in the right place, in the right cluster, where small galaxies were constantly falling into its gravity well. Here's how it works. Imagine two galaxies orbiting each other within a larger cluster. They pass each other repeatedly. Each pass, they exchange gravitational forces. And with each pass, they lose a tiny bit of energy. Over millions of years, they spiral closer and closer. Finally, they collide. But when galaxies collide, something surprising happens. The stars almost never crash into each other. Galaxies are mostly empty space. The stars are separated by such vast distances that when two galaxies merge, the stars just pass through each other like ghosts. But the gas doesn't pass through. When two galaxies merge, the gas smashes together. It compresses. It heats up, and that triggers an explosion of star formation. Billions of new stars forming in a matter of just a few million years. The merger becomes a cosmic fireworks show. But the stars from both galaxies are left in a jumbled, chaotic state. Their organized orbits are destroyed. They're left moving randomly in every direction. And the result is no longer a spiral galaxy. It's an elliptical galaxy, a smooth, featureless structure with stars moving chaotically in 3 dimensions. Now, IC 1101 probably didn't form from a single dramatic merger. Instead, it formed from dozens, maybe hundreds, of smaller mergers over billions of years. A succession of galaxies falling into its gravity well, each collision adding stars, each merger making it larger and more massive. There's a process called dynamical friction that makes this inevitable. Imagine a large galaxy moving through a cluster of smaller galaxies. As it passes each small galaxy, gravity attracts the small galaxy slightly toward the large one. And by Newton's third law, the small galaxy pulls back. The result, the large galaxy slows down. It loses energy. It sinks toward the center of the cluster. Over a few billion years, a massive galaxy starting at the outer edge of a cluster will spiral all the way to the center. And once it's at the center, any other large galaxy that forms nearby will eventually fall into it. The rich get richer. The big get bigger. So the history of IC 1101 is probably something like this. In the early universe, a modest galaxy formed at what would become the center of the Abell 2029 cluster. Over the next billion years, it swallowed dozens of other galaxies. Each merger made it larger. Each collision triggered new starbursts. The galaxy grew and grew. By the time the universe was a few billion years old, IC 1101 had consumed so much material that it had become the dominant galaxy in its region. And by that point, most of the gas had been either converted into stars or blown out of the system. Star formation slowed, then stopped. And since that point, for the last 5 to 10 billion years, IC 1101 has been slowly consuming the remaining satellite galaxies in its orbit, growing incrementally larger, but no longer producing new stars. This growth is actually still ongoing. Even today, small dwarf galaxies are occasionally falling into IC 1101. It's still feeding, still going, still getting larger. We just can't see it happening in real time because the timescales are so vast. But if you could watch IC 1101 for the next billion years, you'd see it visibly accumulate new stars from its neighbors. The question astronomers are wrestling with now is, will this ever stop? Is there a maximum size for a galaxy? Will IC 1101 continue growing until it encompasses its entire cluster? Or will something stop it? And here's where things get really interesting. Because IC 1101 is almost certainly not the end state of galaxy merging. If the Abell 2029 cluster ever merged with a neighboring cluster, IC 1101 might collide with another giant elliptical galaxy. And from that collision, something even more massive would be born. An ultragiant, a structure almost impossible to imagine. But that's probably still billions of years away. For now, IC 1101 reigns as the largest galaxy we know of, and its very existence is a testament to the patient, relentless power of gravity to build structure, collision by collision, merger by merger, over billions of years. 85% of IC 1101 is made of something we've never directly observed, something we don't understand, something that makes up most of the mass in every galaxy, most of the matter in the universe, and yet remains profoundly mysterious. We call it dark matter, and it's one of the greatest unsolved puzzles in physics. Here's the story of how we discovered it. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster. He measured how fast the galaxies were moving, and he found something that shouldn't have been possible. The galaxies were moving too fast. They should have been flying apart, escaping the cluster's gravity. But they weren't. Zwicky concluded that there had to be additional mass. Mass that didn't emit light. Mass that we couldn't see. Dark matter. The astronomical community didn't believe him. It seemed like an extraordinary claim. An invisible substance throughout the universe? That's what you came up with when the math didn't work? But then, 40 years later, an astronomer named Vera Rubin made an observation that couldn't be denied. She studied the rotation of spiral galaxies. Stars in the outer parts of galaxies should move more slowly than stars near the center, just like planets farther from the sun move more slowly than planets closer to the sun. But Rubin found that stars in galaxy outskirts move just as fast as stars near the center. That's impossible. Unless there's a massive halo of invisible matter surrounding the galaxy, pulling on the outer stars and keeping them moving fast. Dark matter was real, and it was everywhere. Today, we know that dark matter makes up about 85% of all matter in the universe. All the stars, planets, gas, and everything you can see makes up only 15%. We live in a universe dominated by something invisible. But what is dark matter actually made of? That's where things get genuinely mysterious. The leading theory is that it's made of particles called WIMPs, weakly interacting massive particles. The idea is that in the early universe, just after the Big Bang, these particles were produced in enormous numbers. As the universe expanded and cooled, they mostly stopped being produced. But they're still around, filling the universe, passing through matter constantly without interacting. Physicists have built incredibly sensitive detectors deep underground, trying to catch dark matter particles bouncing off atomic nuclei. So far, they haven't definitively detected any. But the search continues. Because if dark matter is made of WIMPs, then understanding what they are would revolutionize physics. There are other candidates too. Axions, primordial black holes, exotic particles we haven't even imagined yet. The truth is, we don't know. And that's both humbling and exciting. But here's what we do know. Dark matter was crucial for building IC 1101. In the early universe, dark matter clumped together under its own gravity. These clumps formed the gravitational scaffolding that held galaxies in place. Ordinary matter, gas and dust, fell into these dark matter structures. Stars formed, galaxies assembled, and over billions of years, smaller structures merged into larger ones. IC 1101's dark matter halo is enormous. It extends far beyond the visible galaxy. Some estimates suggest it reaches out 10 million light-years or more from the center. That means the halo is larger than the visible galaxy itself. The halo is what actually holds IC 1101 together. The stars, as numerous as they are, would fly apart without the gravitational influence of all that dark matter. Here's something that really drives home how dominant dark matter is in IC 1101. Even though we estimate the galaxy contains 100 trillion stars, the stellar mass is only 10 to 20 trillion solar masses. That means the average star in IC 1101 is much less massive than the Sun. Most stars are red dwarfs, small and cool and dim. But the total mass of IC 1101, including the dark matter halo, is 100 trillion solar masses, 85 times more massive than all the stars combined. That means if you took every single star in IC 1101, added them all up, and multiplied by 6 or 7, you still wouldn't get the total mass. You'd need the dark matter halo to make up the difference. This tells us something profound about how the universe actually works. It's not built out of the things we can see. It's built out of things we can't see. The visible universe is just the icing on the cake. The cake itself is made of dark matter. And IC 1101 is one of the most extreme examples of this principle. It's a dark matter structure that happens to contain a lot of stars. But the dark matter is the primary component, the dominant structure, the essential ingredient. Now, here's where things get really weird. Scientists have been trying to understand what's inside the dark matter halo of IC 1101. And the computer simulations suggest something unexpected. The halo is lumpy. It has substructure, clumps within clumps. The remnants of smaller dark matter halos that were absorbed when smaller galaxies merged into IC 1101. Some of these dark matter clumps might still contain galaxies, dwarf galaxies, orbiting IC 1101 as satellites. Others might be completely dark, containing no stars at all, just dark matter. Invisible structures exerting gravity on their surroundings, but otherwise undetectable. In some ways, dark matter is the greatest mystery in all of science. We've mapped it. We've measured it. We know roughly where it is and how much of it exists. But we don't know what it is. It's like being able to see the footprints of an invisible person walking around. You know they're there. You can track where they've been, but you can't see them. An IC 1101 is basically a gigantic footprint, a massive structure built by dark matter and gravity, with stars thrown in as an afterthought. Which means that when we study IC 1101, we're not just studying a galaxy. We're studying the fundamental architecture of the universe, the way reality builds its largest and most extreme structures. If you could somehow travel to IC 1101, what would you see? First, you'd see stars, incomprehensibly many stars. So many that if you tried to count them one per second, you wouldn't finish before the sun burns out. The sky around you would be dense with them, not as dense as the core, where the stars form a brilliant, crowded mass, but still so packed that the night sky would never truly be dark. You could read a book under starlight alone, but these wouldn't be vibrant, young stars. These would be old, ancient, tired. Most of the stars in IC 1101 are red dwarfs. Small, cool, dim stars that have been burning their hydrogen fuel for billions of years. These stars will keep burning for trillions of years more. But they're not the bright ones. They're not the ones that catch your eye. What would catch your eye are the red giants. These are stars that have already lived their lives on the main sequence, like our sun, and are now dying. They've exhausted the hydrogen in their cores. The outer layers have expanded, becoming enormous. A red giant star might be hundreds of times larger than it was during its prime, and the surface has cooled, making the star glow with a deep reddish light. From far away, IC 1101 as a whole has a yellowish red color. It's not blue like young star-forming galaxies. It's not the bright white of a galaxy full of young hot stars. It's the warm, ancient color of a galaxy that finished making stars billions of years ago. Here's the thing that really gets you when you think about it. When astronomers study the spectrum of IC 1101, they see no signs of ongoing star formation. There are no young hot stars. There are no emission lines indicating gas being ionized by ultraviolet radiation from newborn stars. There are no nebulae, no nurseries where new stars are being born. IC 1101 is sterile. It's a galaxy that has entirely finished the process of making stars. All the stars that are going to be born have already been born, probably billions of years ago. This is remarkable because most galaxies are still forming stars. The Milky Way is still forming stars. There are regions of our galaxy right now where gas is collapsing, forming new stars, where the process of stellar birth is ongoing. Andromeda is still forming stars. Most galaxies we observe are still actively engaged in star formation. But IC 1101 is not. It's past that phase. It's entered what astronomers call the red and dead phase. All red because of the old stars, all dead because of the lack of ongoing star formation. When you analyze the ages of stars in IC 1101, using something called color magnitude diagrams, you find that most of them are around 12 to 13 billion years old. The universe is only 13.8 billion years old. These stars formed when the universe was barely a few billion years old. They've been shining for over 90% of cosmic history. To put that in perspective, the Sun is 4.6 billion years old. The oldest stars in IC 1101 are almost 3 times as old. They were shining before Earth even existed. This tells us something crucial about IC 1101's history. The galaxy formed most of its stars very early, during what astronomers call cosmic noon, when the universe was young and full of gas and dust, ready to make stars. Since that time, something has happened to shut down star formation. The gas got used up, or it got blown away, or it got stripped out by interactions with other galaxies. And once star formation stopped, IC 1101 could never really resume it. A galaxy needs gas to make stars, gas to collapse under gravity, gas to form protostars. IC 1101 has almost no gas left. It's been consumed or expelled or lost. So the galaxy is locked in its current state, slowly aging, slowly dimming. What makes this really poignant is the thought of what comes next. All those red giant stars that are visible right now, they're dying, not in the next few years or decades, but over the next few million years. One by one, they'll exhaust their fuel. They'll shed their outer layers into space, creating planetary nebulae, those beautiful glowing rings of gas around dying stars. And what's left will be a white dwarf, a dense core about the size of Earth, but containing the mass of the Sun. Those white dwarfs will cool very slowly, incredibly slowly. A white dwarf cools so gradually that one that's been around for billions of years might still be several thousand degrees hot. Over trillions of years, it might cool to room temperature. And eventually, given enough time, it would cool so much that it stops emitting detectable radiation. We call these black dwarfs. A black dwarf is just a dead star, cold and dark, invisible except for its gravity. And that's the fate of IC 1101. Not dramatic, not spectacular, just a gradual fade into darkness. One star at a time, over billions and billions of years. IC 1101 will dim. Its once vibrant light will fade, until eventually it's just a vast, invisible halo of dark matter dotted with countless cold, dark stellar remnants. But that's not going to happen for a very long time. For now, IC 1101 is still there, still shining, still visible to our telescopes. An archive of cosmic history, frozen in the light of 100 trillion ancient stars. At the very center of IC 1101 is something almost impossible to comprehend. A black hole so massive that it's difficult to grasp the actual scale of what you're talking about. We're talking about a black hole containing somewhere between 40 and 100 billion solar masses. That's not a typo. 40 to 100 billion times the mass of our Sun, concentrated into a point so small that the event horizon, the boundary from which nothing can escape, is only a few billion kilometers across. To give you some perspective, the Sun is about 1.4 million kilometers in diameter. A black hole with 100 billion solar masses would have an event horizon about 2,000 times larger than the Sun. 2,000 times. An object of almost incomprehensible scale. And yet, from a distance, it's completely invisible. You could point a telescope right at it and see nothing. Not because it's small, but because no light can escape it. It's black by definition. A hole in the fabric of reality where the normal rules of physics break down. How does a black hole this massive even form? That's one of the great questions in astronomy. Stellar black holes, the ones formed from the collapse of individual massive stars, typically have masses between 5 and 20 solar masses. Even the biggest stellar black holes we've found are only a few dozen solar masses. But supermassive black holes are millions or billions of times more massive. How did they grow so large? The leading theory is called hierarchical black hole growth. It works like this. In the early universe, stellar black holes form from dying massive stars, just like they do today. But in the dense, chaotic early universe, black holes sometimes encounter each other. And when they do, gravity causes them to merge. Two black holes become one larger black hole. Additionally, black holes can consume gas. When gas falls into a black hole, the black hole feeds. The black hole grows more massive. Over billions of years, through repeated mergers and repeated feeding on gas, a stellar black hole could grow into a supermassive black hole. And here's the kicker. The growth is accelerated in the centers of galaxies, especially during galaxy mergers. When galaxies collide, gas gets channeled toward the center. The black holes at the centers of the two galaxies sink toward each other. Eventually, they merge. The resulting black hole is larger, and it has access to enormous amounts of gas to feed on. So the history of IC 1101 central black hole is probably something like this. An original stellar black hole forms from a dying star billions of years ago. As galaxies merge into the proto-IC 1101, they bring their own central black holes. These black holes sink to the center. They merge with the existing central black hole. The result is a larger black hole. And this process repeats over and over with each galaxy merger, each time producing a larger black hole. After enough mergers, you end up with something monstrous. Something with a mass of tens of billions of solar masses. Something that has consumed the black holes from hundreds of thousands of galaxies. Now here's what's remarkable. We've actually observed the effects of this ultramassive black hole, even though we can't see the black hole itself. Stars near the center of IC 1101 move incredibly fast. We're talking about tens of thousands of kilometers per second. Stars moving that fast are orbiting an incredibly massive object. By studying the orbits of these stars, by measuring their velocities and extrapolating backward, astronomers can calculate how much mass is at the center. And all the calculations point to the same conclusion. There's a black hole there. A black hole with tens of billions of solar masses. But here's the truly remarkable thing. This black hole is probably dormant. It's not actively feeding. It's not producing the intense radiation that active black holes produce. It's just sitting there, dormant, quiet. In the early universe, many black holes were active. They consumed gas at prodigious rates. They shone as quasars, some of the brightest objects in the entire universe. A single active black hole could outshine an entire galaxy. But as the universe aged, most black holes ran out of fuel. The gas was used up, and the black holes went quiet. IC 1101's black hole probably went quiet billions of years ago. It's been dormant ever since. No bright jets of particles shooting out at near light speed. No intense radiation heating the surrounding gas. Just a quiet, massive object sitting at the center of the galaxy, exerting gravitational influence on the stars around it, but otherwise invisible. Which raises a profound question. What's the ultimate fate of this black hole? Will it ever feed again? Will it ever light up as an active nucleus? Or will it remain dormant, slowly accumulating mass as stars occasionally wander too close and get torn apart by tidal forces? And here's something even more thought-provoking. What happens on even longer timescales? In the far future, trillions of years from now, after all the stars in IC 1101 have burned out, what happens to this black hole? According to some theories in physics, even black holes eventually evaporate. They emit radiation, slowly losing mass over incomprehensibly long timescales. A black hole of 100 billion solar masses would take roughly 10 to the 100th power years to evaporate. That's a 1 followed by 100 zeros. The current age of the universe is only about 1 billion years. So IC 1101's black hole wouldn't finish evaporating until incomprehensibly far into the future. But that's what's remarkable about studying IC 1101. It forces you to think on timescales that are almost impossible to visualize. Billions of years for stars to form and age. Trillions of years for those stars to burn out. Incomprehensibly larger numbers for black holes to evaporate. It's a perspective that makes you realize how ephemeral everything is, from our own existence to the existence of stars themselves. IC 1101 doesn't exist in isolation. It's the most massive object in the Abell 2029 galaxy cluster. And around it, orbiting in its gravitational field, are hundreds of other galaxies, most of them much smaller. Imagine a cosmic city where IC 1101 is the center building, so enormous that it dominates everything around it. But around it are thousands of other buildings, millions of people, all functioning within its gravitational influence. The Abell 2029 cluster is one of the richest known galaxy clusters. It spans millions of light years. It contains hundreds of galaxies. And the density of galaxies is so high that in a region of space that would be almost empty if you looked at it from a typical location in the universe, you're instead surrounded by galaxies in every direction. The cluster is held together by gravity. All that matter, all those galaxies, all the dark matter between them, creates a gravitational field so strong that nothing can escape. The galaxies orbit each other in this field, sometimes accelerating, sometimes slowing down, but always bound together. And IC 1101, with its enormous mass, sits at the very center of this cluster. It's the gravitational anchor, the king. Now here's what's fascinating. The smaller galaxies are still falling into IC 1101, literally, due to a process called dynamical friction. Smaller galaxies gradually lose orbital energy. They spiral inward, and eventually they collide with IC 1101 and merge. This process is ongoing. Even today, small dwarf galaxies are orbiting IC 1101, slowly spiraling inward. Eventually, they'll crash. They'll merge. Their stars will be absorbed into IC 1101, and IC 1101 will grow even larger. But here's the thing that really gets you. This process of merging galaxies is so slow that we can't see it happening in real time. We can't watch a dwarf galaxy spiral into IC 1101. It would take millions of years. But if you could speed up time, if you could watch IC 1101 over a billion-year period, you'd see it visibly accumulating stars from its neighbors. The cluster also has another feature: hot gas. Incredibly hot gas, temperature millions of degrees. This gas, called the intracluster medium, fills the spaces between galaxies. It was heated by gravitational energy released as the cluster formed and galaxies fell into it. This hot gas has a profound effect on the smaller galaxies. As a galaxy moves through the hot gas, the gas creates a pressure, like the wind you feel when you drive a car with the windows down. If this ram pressure is strong enough, you can strip gas out of galaxies. The gas gets pulled away. The galaxy loses its ability to form new stars. This process is called ram pressure stripping, and it's probably one of the reasons IC 1101 and other giant ellipticals have stopped forming stars. They've been stripped of gas. The cluster is also not static. It's a dynamic system, constantly evolving. Galaxies are moving. The cluster is probably merging with neighboring clusters. Over cosmic time, clusters merge to form superclusters, and superclusters eventually merge to form the largest structures in the universe. So the Abell 2029 cluster, with IC 1101 at its heart, is just one node in a vast cosmic web. A node that's connected to other nodes through filaments of dark matter and galaxies. All of it bound together by gravity. All of it slowly evolving, slowly changing, over billions of years. What's remarkable is that despite being the largest structure known, IC 1101 isn't the largest thing in its cluster. The cluster as a whole is larger, and the supercluster that contains the cluster is even larger. And if you zoom out far enough, you see that the entire observable universe is interconnected through a cosmic web of filaments and voids. A web so large and so complex that it almost defies visualization. But all of this immense structure is held together by gravity, by the simple fact that mass attracts mass, that stars fall toward each other, that galaxies cluster together, that the universe builds structure, bit by bit, merger by merger, over billions of years. IC 1101 is just an extreme example of this process. The ultimate expression of what happens when you have enough gravity, enough time, enough mass, all in one place. Let's step back for a moment and ask a fundamental question. How do we know IC 1101 is actually real? How do we know our measurements are correct? How do we know we're not making some kind of systematic error? This is important to ask because IC 1101 is so extreme, so far outside normal experience, that it's worth checking our work. How did we measure its size? How did we measure its distance? How did we measure its mass? And most importantly, can we be sure? For the size, it's relatively straightforward. We take an image of IC 1101. We measure how many pixels it takes up on the image. We know the angular resolution of our telescope. We can convert pixels to angles on the sky. So we can measure how many arc minutes wide IC 1101 appears to be. That's the easy part. The hard part is converting that angular size into actual physical size. And that requires knowing the distance. If IC 1101 is farther away than we think, then it's larger than we think. If it's closer, then it's smaller. So the distance measurement is crucial. And the distance measurement comes from multiple independent techniques. We have the Faber-Jackson relation, which uses the velocity dispersion of stars to predict the intrinsic brightness, and compares that to the apparent brightness. We have redshift measurements using Hubble's law. We have gravitational lensing studies, which directly measure how much mass is bending light, allowing us to estimate distance indirectly. All of these techniques give approximately the same answer. IC 1101 is about 1.07 billion light-years away. The fact that different techniques agree is a good sign. It suggests we're onto something real, but let's dig deeper. Is there any possibility we're wrong? Is there any systematic error we might be missing? One possibility. What if IC 1101 is actually much closer, and we're just misinterpreting the data? If IC 1101 were only a few 100 million light-years away, instead of 1 billion, it would be smaller than we think. Not as record-breaking. Still huge, but less extreme. But this seems unlikely. The redshift of IC 1101 is well measured. Multiple spectroscopic surveys have confirmed it. If IC 1101 were closer, its redshift would be lower. But it's not. The data is consistent. Another possibility. What if some of what we're seeing as IC 1101 is actually background galaxies, or foreground galaxies, that just happen to be aligned with it? What if the actual IC 1101 is smaller, and we're overestimating its size by including other objects? This is a more serious concern, and it's something astronomers have to be careful about. When you're looking at an extremely faint object like IC 1101, it's easy to get confused about what you're actually seeing. But multiple deep surveys of IC 1101 have been conducted using different telescopes, and they all find the same basic structure: a large elliptical galaxy with an extended halo. So we're probably not confusing IC 1101 with something else. It's real. It's there. It's as large as we think. What about the mass? Is our mass estimate reliable? Here, the evidence is even stronger. We have multiple ways of measuring it. We can measure the velocity dispersion of stars and calculate the mass needed to hold them in orbit. We can use gravitational lensing to directly map the mass distribution. We can use X-ray observations of the hot gas to calculate the gravitational field. And all of these techniques give similar answers. So the mass of IC 1101 is probably close to what we think. 100 trillion solar masses, give or take. Now, here's something interesting. There are actually a few other galaxies that are potentially as large as or even larger than IC 1101, depending on how you measure them. Holmberg 15A is often cited as a potential contender. A 2261 BCG is another. ESO 306-17 is another giant elliptical. The measurements of these galaxies are not as well constrained as IC 1101 because they're more distant or more difficult to observe, but they're all in the same ballpark. All somewhere in the range of a few million to 10 million light years across, which raises an interesting question. Is there some maximum size that a galaxy can reach? Is there a limit to how large gravity can build a structure? And the answer is probably yes. If a galaxy gets too large, the outer parts would be moving so fast that they'd escape the gravitational field. The galaxy would be unstable. It would fall apart. There's probably a maximum size somewhere around 10 million light years. And IC 1101 at 6 million light years is close to that limit. But the fact that we're finding multiple galaxies near that limit suggests that we're looking at the extreme end of the galaxy size distribution. These aren't normal galaxies. These are the largest objects that gravity can build before the structure becomes unstable. And that tells us something profound about how the universe works. There are limits to how large structures can get. There are limits to how dense they can become. The universe has a maximum size for galaxies, a maximum brightness, a maximum mass. And IC 1101 is pushing against those limits. Let's put IC 1101 in context by comparing it to other galaxies we know. Start with the Milky Way. Our galaxy is often considered a large spiral galaxy. It contains an estimated 200 to 400 billion stars. It spans about 100,000 light years. It's impressive by normal standards. But compared to IC 1101, the Milky Way is a dwarf. IC 1101 is roughly 300 times more stars. It's 60 times wider. If you took the Milky Way and shrunk it down to the size of a grain of sand, IC 1101 would be the size of a beach ball. Now let's consider Andromeda, the nearest large galaxy to the Milky Way. Andromeda is actually a bit larger than the Milky Way in some measurements. It might contain up to 1 trillion stars. It's about 200,000 light years across. Still impressive, but compared to IC 1101, Andromeda is small. 100 times fewer stars, 1/30th the width. If you replace the Milky Way with IC 1101, the combined Milky Way-Andromeda system would fit entirely within IC 1101's diameter. Now, IC 1101 isn't alone at the top of the galaxy size charts. There are other giant ellipticals. Holmberg 15A is sometimes cited as potentially larger than IC 1101. It's about 1 billion light years away. Its stellar halo extends to tremendous distances. Some measurements suggest it could be as large as 8 million light years across, or even larger depending on how you measure it. But these measurements are less well constrained than IC 1101's. A 2261 BCG is another giant elliptical. It sits at the center of the Abell 2261 cluster, just like IC 1101 sits at the center of Abell 2029. A 2261 BCG might be 3 billion light years away. It's a bit smaller than IC 1101 in most measurements, with a diameter of maybe 2 to 3 million light years. ESO 306-17 is another colossal elliptical. It's about 1.5 billion light years away. Its light is spread incredibly thin. It's actually quite faint, because all its light is distributed over such a vast volume. There's also a galaxy called Alcyonius. Now, Alcyonius itself isn't as large as IC 1101 in terms of its stellar body, but Alcyonius has something remarkable: enormous radio jets. The jets from the supermassive black hole at its center extend to over 16 million light years. That's more than 2.5 times the width of IC 1101. So in terms of total extent, including the jets, Alcyonius might actually be larger than IC 1101. But when we talk about IC 1101 being the largest galaxy, we're specifically talking about the stellar body, the actual stars, the galaxy's main visible structure. And in that measure, IC 1101 holds the record. What's remarkable is that all of these giant ellipticals are found at the centers of galaxy clusters. There's a pattern here. The largest galaxies are central dominant galaxies in clusters. They're not found in isolation. They're not found in pairs. They're found surrounded by hundreds or thousands of smaller galaxies, all orbiting them, all gradually falling into them. This tells us something important about how galaxies reach extreme sizes. You can't get to IC 1101 size by just existing in the field, isolated from other galaxies. You need to be in a dense cluster. You need to have a constant supply of smaller galaxies to cannibalize. You need billions of years of mergers and accumulation, which means that IC 1101 size is not an accident. It's the natural outcome of gravitational dynamics in a rich galaxy cluster. It's what happens when you have the right conditions, the right environment, the right amount of time. What happens next? We've looked at IC 1101's past. We've understood how it grew to this enormous size. But what about its future? The short answer: IC 1101 will continue as it has been. Over the next billion years, it will continue to slowly accumulate smaller galaxies from the Abell 2029 cluster. It will grow slightly larger. Its stellar mass will increase. But the rate of growth will be slow, because there's a limit to how many galaxies remain in a cluster that are smaller than IC 1101. It's already eaten most of them. But here's where it gets interesting. Eventually, over timescales of many billions of years, the Abell 2029 cluster might merge with nearby galaxy clusters. When that happens, new giant galaxies would come into the region, and IC 1101 might collide with one of them. What would happen if IC 1101 merged with another giant elliptical, say something like Holmberg 15A? The result would be unimaginably massive. A structure so large it would approach or perhaps exceed the theoretical limit for a single gravitationally bound galaxy. We're talking about an ultra-giant elliptical, a structure that might span 10 million light years or more. Would such a merger be violent? Absolutely. Not in the sense of stars colliding, because stars almost never hit each other, even in galaxy collisions. But in the sense of gravitational disruption, stars would be thrown into new orbits. Tidal forces would stretch and contort the structure. The merger would take hundreds of millions of years. And when it was over, the result would be something almost beyond human comprehension. But we're probably talking about a timescale of at least tens of billions of years before that happens. Maybe hundreds of billions. It's not imminent. Over the next 100 billion years or so, IC 1101 will slowly dim. The red giant stars, visible now as the galaxy's most prominent features, will gradually burn out. One by one, they'll shed their outer layers as planetary nebulae, leaving behind white dwarfs. The red dwarfs, which make up most of the stellar population, will keep burning, but they'll do so very slowly, fading almost imperceptibly. The galaxy will become dimmer and dimmer. If a hypothetical astronomer were observing IC 1101 at that point, they'd need increasingly sensitive telescopes to detect it. The light output would be a fraction of what it is now. Over trillions of years, essentially all the stars in IC 1101 would have burned out. The red dwarfs, the longest-lived stars, would finally exhaust their hydrogen fuel. What would remain would be a vast cloud of stellar remnants, white dwarfs, the exposed cores of dead stars, neutron stars, the ultra-dense remnants of massive stars. Black holes, where the most massive stars have collapsed. And this cloud of stellar remnants would be so spread out, so sparse, that interactions between objects would become incredibly rare. The galaxy would exist as an extremely diffuse collection of dead matter, held together only by gravity. Then, over incomprehensibly long timescales, according to certain theories in physics, even the black holes would evaporate. Stephen Hawking proposed that black holes are not truly eternal. They emit radiation, lose mass, and eventually completely evaporate. For a supermassive black hole like the one at IC 1101's center, this would take roughly 10 to the 100th power years. That's a 1 followed by 100 zeros. The current age of the universe is less than 10 to the 10th power years. So we're talking about a timescale that's 90 orders of magnitude longer than the entire history of the universe so far. But eventually, even that would happen. The black hole would evaporate. IC 1101 would cease to exist as a distinct structure. Its stellar remnants would be scattered across space, moving very slowly under their mutual gravity, gradually dispersing. And so the fate of IC 1101 is essentially that of all structures. It will fade, it will cool, it will age. It will eventually dissolve into the heat death of the universe, not dramatically, not quickly, but inevitably. But that's billions or trillions of years away. For now, IC 1101 shines. 100 trillion stars, each one a sun, lighting up the cosmos. Each one a potential home for worlds we'll never know. Each one a story we can never fully tell. So what do we take away from this? What does IC 1101 teach us? First, IC 1101 teaches us that the universe builds structures on scales that are difficult for human minds to comprehend. 6 million light years, 100 trillion stars, hundreds of billions of solar masses. These numbers are so large that they barely register emotionally. We understand them intellectually, but we can't truly feel them the way we feel the size of a mountain or the distance to the stars. This is important because it suggests something humbling. Our intuitions about size and scale are shaped by our evolutionary history. We evolved on a planet. We're used to thinking about distances measured in meters and kilometers. Our brains are built to process the world at human scales. But the universe doesn't care about human scales. It builds structures that are utterly alien to our experience. Second, IC 1101 teaches us that the universe has no upper limit on size. There's no law of physics that says a galaxy can't be this big. There's probably some practical limit, some point beyond which gravity would be too weak to hold a structure together against cosmic expansion. But we haven't found that limit. And IC 1101 shows us we're getting close. Third, IC 1101 teaches us about the power of time. Nothing about IC 1101 was built quickly. Every galaxy that merged into it took millions of years to spiral in. Every merger took hundreds of millions of years to complete. The whole process took billions of years. But given that much time, gravity can build something astonishingly large. Fourth, and perhaps most profoundly, IC 1101 teaches us about our place in the universe. The Milky Way is a large galaxy by typical standards. The Sun is a medium-sized star. Earth is a small planet. Humanity is a young species, barely a blink in cosmic time. When you put IC 1101 into the picture, you realize how utterly insignificant we are. But here's the thing, that insignificance is not depressing. It's liberating. It means that our petty concerns, our conflicts, our individual struggles, are all happening within a context so much larger than ourselves that they cease to matter on cosmic scales. The universe will continue long after humanity is gone. Galaxies will merge. Stars will burn out. The universe will eventually cool and die. None of it depends on us. None of it cares about us. And somehow, that's comforting. It puts things in perspective. Our problems are real, and they matter to us. But they're local. They're temporary. In a billion years, none of it will matter. Fifth, IC 1101 reminds us of how much we still don't understand. We don't fully understand how IC 1101 grew so large. We don't know what dark matter is, and yet dark matter makes up most of IC 1101's mass. We don't know if there are structures even larger than IC 1101, hidden somewhere beyond our observable universe. We don't fully understand black holes, or the ultimate fate of galaxies, or the nature of consciousness in a universe this large. There are mysteries, deep mysteries, And those mysteries are what drive science forward, because humans are curious. We want to know. We want to understand. That's what this whole exploration has been about. Not just IC 1101 itself, but the fundamental human drive to look up, to ask questions, to push our knowledge to its limits. IC 1101 is a monument to that drive. It's a structure so large that it challenges our understanding, so old that it reminds us of cosmic history, so massive that it forces us to confront the limitations of human comprehension. And yet, we can understand it. We can measure it. We can study it. We can ask intelligent questions about how it formed and what happens next. That ability, that drive to understand something so far beyond us, is perhaps the most remarkable thing about consciousness itself. We are the universe experiencing itself, trying to understand itself, building telescopes and computers and theories to make sense of the cosmos. IC 1101 exists 1.07 billion light years away. The light we're seeing from it has been traveling for over 1 billion years. It passed through countless galaxies. It narrowly avoided black holes. It survived cosmic encounters we can barely imagine. And it reached our telescopes, allowing us to see this thing, to measure it, to marvel at it. That light is a connection across inconceivable distance and time, a bridge from here to there, from now to then. And through that light, we can reach across the cosmos and touch the edge of reality. But here's something that might actually shock you. Here's the thing that really drives home just how extreme IC 1101 is. Are you ready for it? IC 1101 is almost certainly not the largest galaxy that exists. Think about that for a moment. We've been exploring the largest galaxy we know about, the record holder, the champion. And it's probably not actually the largest one out there. See, we can only observe a limited portion of the universe, the observable universe, the part of the cosmos that's close enough for light to have reached us since the Big Bang. Beyond that, there could be anything. There could be galaxies twice the size of IC 1101. There could be galaxies 100 times the size. We have no way of knowing because the light from those galaxies hasn't reached us yet. It's still traveling toward us through the expanding universe. And by the time it does reach us, billions of years from now, those galaxies will have continued growing, merging with other galaxies, accumulating more stars, becoming even larger. The universe is almost incomprehensibly vast. Our observable universe is about 90 billion light years across. That's the distance from here to the edge of the observable universe. But the actual universe, according to current theories, is at least 1,000 times larger. Maybe 1,000,000 times larger. Maybe infinitely large. We don't know. And in that vast universe, there could be structures beyond anything we can imagine. Objects so large that IC 1101 would look small by comparison. Phenomena so extreme that they'd challenge our understanding of physics itself. That's the thing about exploring the cosmos. Every time you think you've found the edge, you realize there's more. Every time you think you've found something so extreme that it must be unique, you find something even more extreme. IC 1101 is the largest galaxy we've discovered. But it's not the final answer. It's a waypoint, a stopping point on a journey that's essentially infinite. There's always more to explore, always more mysteries to uncover, always deeper questions to ask. And that's what drives science forward. That's what drives curiosity. The realization that no matter how far you go, no matter how much you discover, there's always something beyond. Always something else to wonder about. IC 1101 represents the edge of what we can currently observe and measure and understand. But it's not the edge of what exists. It's just the edge of what we can see right now, with our current technology, from our particular vantage point in the universe. And that's simultaneously the most humbling and the most exciting thing about studying astronomy. We live in a universe so vast, so complex, so fundamentally alien to human experience that we'll probably never fully understand it. But that doesn't stop us from trying. That doesn't stop us from building better telescopes and asking smarter questions and pushing the boundaries of human knowledge further and further. IC 1101 is a testament to that drive. A structure so enormous that it stretches human comprehension to the breaking point. And yet we persisted in studying it. We measured it. We calculated its mass. We traced its history. We pondered its future. And through that process, we learned not just about IC 1101, but about ourselves, about what we're capable of understanding, about how powerful the human mind is when it's driven by curiosity and wonder. So where does that leave us? We spent the last several hours exploring IC 1101, the largest galaxy we know of, a structure so vast that it challenges human comprehension, so ancient that it carries within it the history of cosmic structure formation, so massive that it reminds us of our own insignificance. But as you sit here at the end of this journey, I want you to think about something. Yes, IC 1101 is enormous. Yes, it dwarfs anything we can imagine. Yes, it's probably going to keep growing for billions of years. Yes, there's probably something even larger that we haven't discovered yet. But here's the thing that matters. We know it exists. We can see it. We can study it. We can ask questions about it and get real answers. That ability, that power to understand something so far beyond ourselves, is remarkable. In medieval times, people used to wonder what was beyond the edge of the known world. There were maps that said, "Here be dragons," at the borders of explored territory. And people wondered and worried about what mysteries lurked beyond. We still wonder. We still worry. But now we have better tools. Now we have telescopes that can see 1 billion light years into space. Now we have physics that can explain how structures this large form. Now we have computers powerful enough to simulate the mergers of galaxies. But the wonder, the sense of awe, the feeling that we're touching the edge of something profound, that's still there. That will probably never go away as long as humans look up at the night sky and ask questions. IC 1101 reminds us of that wonder. It reminds us that there are mysteries left, that there are structures so enormous they seem to defy comprehension, that the universe is stranger and vaster and more profound than our everyday experience suggests. If you've watched this far, if you've stuck with me through billions of light years of cosmic exploration, then I want to thank you. Thank you for being curious. Thank you for caring about these mysteries. Thank you for trying to understand the cosmos, even though it's so far beyond our normal experience. You should definitely subscribe to the channel if you haven't already. Hit that bell to get notifications whenever we upload. Drop a comment and tell me, what aspect of IC 1101 shocked you the most? Was it the size, the age, the number of stars, the dark matter halo? Or was it the realization that something even larger might be out there? I read every single comment, and your questions and observations often guide what we explore next. This channel exists for people like you, people who look up at the night sky and wonder, people who want to understand the universe, even though it's so profoundly strange and vast. The universe is big, incomprehensibly big. It's old, unimaginably old. It's full of mysteries and wonders that we're only beginning to understand. IC 1101 is just one piece of that puzzle. One example of how extreme reality can be. One reminder that the universe doesn't follow our intuitions. It builds structures on scales we can barely fathom. But that's what makes it worth exploring. That's what makes it worth studying. That's what makes it worth dedicating your life to understanding. Thank you again for joining me on this journey. Thank you for caring about IC 1101. Thank you for wondering about the cosmos. Keep looking up. Keep asking questions. Keep pushing the boundaries of human knowledge. Because the universe is waiting, and there's always more to discover.